Now here is a set concept, and this probably have a definition. A set is a collection of objects called elements or members. I may use elements or members for the objects that we have in set. And example is if the set is MJC courses, the elements or members will include Math 101 and all other courses offered at MJC. So what we have here is the members or elements would be 2, 4, 6, 8, 10, 12. So these, what they have here using this dots, what that means we have infinite set. So we have infinite, and here well defined if its elements can be clearly determined. So example, the set of classes at MJC is well defined. For example, you can have this class over class Math 101. For example, Math 89. So all classes. So 3 dots, we have infinite. Because I'm not sure how many we have here. That's why I'm using 3 dots. But obviously we have, we can count them. But here in this case, I'm not using that because I'm not sure how many we have. And maybe semester by semester they're changing it. So that's why we're using 3 dots. But we are able to know to find out what classes we have. That's why this is well defined. Now here is mathematician. Later we're gonna work on 2-page math reports. It's better to know all these mathematicians. Here we have this mathematician is recognized as a father of modern set theory, the Cantor set, named after him. So here's one mathematician. You can use this one to write your report. Later we're gonna have more. So there are 2 ways to express a set. We have roster form and also set builder form. For example, set of natural numbers, it's n, that is equal to, here is set, starting with 1, 1, 2, 3, 4, and here is infinite. This is roster form. And that are less than 9, so these are less than 9. Okay, no, these, okay. So the set of natural numbers that are less than 9 can be expressed in roster form. So here is roster form. We have that one, and these numbers are less than 9. And in set builder form, now we have this part. So using the same example that we have here, which was in roster form, now writing that one in set builder form. So we have x such that, like this vertical line, that is called such that. So that is such that x belongs to, so this is this one is called belongs to. So x belongs to natural numbers is less than 9. Okay, that is less than 9. Where x belongs to natural numbers means we can also write this way. So x is an element of natural numbers. So when we had this is finite set. So it's not infinite. This one is infinite. Because here we are not sure how many numbers we have after that 4. So it's infinite. Now other way to write that one is the set builder as set x such that x belongs to natural numbers and x is less than 9. Now next part, two sets are equal if they contain the exact same elements. Example, for example, I have set A is equal to 1, 2, 3, and B again 1, 2, 3. Since we have exactly the same thing, that means that these two sets are equal. So A is equal to B. We should have exactly the same elements. We have 1, 2, 3, 1, 2, 3. Now next one, the cardinal number or cardinality of the set is the number of elements. So this is the number of elements in that set, showing with this is the number of elements in set A. For example, I have this set 1, 2, I have 4, and the number of elements is set A. So this is number of elements in this set is equal to, you have to count how many members you have here inside the set is 1, 2, 3. You have 3 elements. Another example here is, for example, B is 3, 5, 6. And based on that, number of elements in set B is equal to 1, 2, 3. So here again we have 3 members. Now in this part we have two sets A and B are equivalent if and only if number of elements in set A is equal to number of elements in set B. See, I got same thing, meaning that number of elements in set A is equal to number of elements in set B, and that was equal to 3. So this is also an example for this part. Now, two sets that are equivalent can be placed in one-to-one correspondence, which means that each element of set A is matched with exactly one element of set B using defined map. Okay, I'm using same example that I used here. Here I have set A, set B, and for A we have 1, 2, 4, and B is 3, 5, 6. We have these members here inside. Now it says that these two sets are equivalent if you have one-to-one correspondence. So one-to-one correspondence meaning like that. So 1, 2, 3, 2, 4, 2, 2, 5, and 4 to 6. And here we have 1-to-1. Correspondence between A and B. Now here is the empty set, is the set with no elements. So no elements, and is symbolized by, here we have set, we have nothing inside, so that is empty set. Or this one is for empty set, so this is empty set. Now next one is a universal set showing with U. It's a set that contains all elements for any specific discussion. Okay, I have example for this part. For example, here is A, B, C, D. Set B is A, B, E, and C is D, E, F, G. So we have 3 sets. So this part's given. So let's say that this is given. This part given. And I want to find what the universal set is. So for universal set, that contains all elements in all these 3 sets, set A, B, and C, but do not repeat. So we're not repeating it. We have A, B, C, D. Here again we have A, B, so I'm not rewriting it. A, B, C, D. And after that we have, here again we have D, so we already have that part here, so I'm not rewriting it. And after D we have E, F, G. So this is the universal set as A, B, C, D, E, F, G. Having all the members that we have inside all these 3 sets. Now, example, determine if each set below is well defined, meaning that are we able to find out what elements we have. So set is well defined if its elements can be clearly determined. So that is the definition for the operators. And also we want to see if this is infinite or finite. Part A, the set of odd natural numbers. We have odd natural numbers starting with 1. After that, 1 plus 2 is 3. Plus 4 plus 2 again, we have 5, 7, 9. So these are odd natural numbers. Obviously, we know what numbers we have here, meaning that this is well defined. And how many numbers we have here, it's not stopping here though. We're not sure how many numbers we have, meaning that this is infinite. So it's well defined and infinite. Now part B, the set of best movies of 2019. So best movies of 2019. We don't know what movies are exactly the best ones in 2019, and it didn't say in what country or where that is. Meaning that I'm not sure what those are, meaning that this is not well defined. We may have different ideas on what movies are the best, so that's why this is not well defined. So having different ideas. but so we may have different ideas, but here obviously we have list of best movies, so this is finite. So it's not well defined, but it's finite. And part C, the set of that's when we have all these numbers. Since we have all these numbers, again, obviously this is well defined. And this is infinite. What we have here is 1 square, 2 square, 3 square, 4 square, 5 square, and 6 square. Now part is the smartest people who ever lived. So again, this is something like part B. So again is not well defined, because we have different definition of what smart means. We may also have finite or number of members or infinite number of members. So either one works, but the point is we don't know what exactly we have in that set. We don't know what our members are. So not well defined. And this part we can have infinite or finite depending on how you define it. So we have different definition of what smart means. You may think, okay, we have all of us here in this class are smart, but another person may say, okay, no, all mathematicians are smart. So that's why we may have different type of ideas, and our answers will differ based on that. If we say that our classes, we have all smart people, and we know that, okay, other class, they also have smartest people. So because of that, we're not able to count them. So that will be infinite. But if we say that, okay, all mathematicians are smart, so what we had in history, that list, we can have a list of those people, and that will be finite. For that reason, we can also have finite and infinite, or we can also have finite, so there is no correct answer for this part. No one, we do not have only one correct answer. We may have different one. So we may have finite number of members. So in this case, both of these works. Now example number 2. Express each of the following sets in roster form. So here, instead of that, I'm going to use roster form. So this is set of all x such that, so this is set of all x such that x minus 5 equal to 11. I should find x first. Solving for x. X is 16. So this is the only number that we have here. X is a 16. So writing roster form is, this is a, that is equal to, now we have 16, and that's it. B set of months, name begins with letter J. Here only use set E, because it didn't say what set is, but I want to make it easier, so let's use B. And our roster form is Almost not starting with J. January, June, July. So it's this one. This is the answer. And this was the answer for top one. And it didn't ask us, but what if the question was how many members we have here inside? Number of elements in set B is 1, 2, 3. So it didn't ask us, but I'm writing it. Cardinality. The number of elements in B is equal to 3. So you have to count how many numbers you have here. Now part C, set of Professor Chatham JC for less than 9 years old. So that is typo. Obviously, we do not have less than 9 years old, meaning that here is empty set. So this is also form, and we have nothing inside, so this is empty set. So that is exactly the same as signing this for empty set. But since it's asking to write Russell form, this will be the answer. For D, x such that x belongs to natural numbers and x is between 2, 15. Here we do not have equal to, but here we have equal to. Since we do not have equal to, meaning that x is greater than 2 and that starts with 3. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this is equal to, so it's equal to 15. This is the answer for this part. And here x belongs to natural numbers and x is odd. So this is easy. We have odd natural numbers. Now example number 3, express each of the following set in set builder notation. Now instead of having roster form, now we have set builder notation. The first one is set of national holidays in the United States in May. So first, I'm going to define variable with HB holidays because we have international holidays and X holidays in May. And the answer is X such that X, that is X holidays in May, belongs to holidays, so national holidays, and that X is Memorial Day. So this is set builder. Now part B, set up odd natural numbers. X such that we have natural numbers and it's odd. We can write in words like this, and X is odd. So this is set builder. And part C, we have these numbers, but these are X such that, again, these are natural numbers, so X belongs to natural numbers, but these numbers are greater than, so these are numbers are greater than equal to 4. And part D, here we have these numbers 4, 8, 12, 16, 20, 24, where these can add 4. So 4 plus 4 is 8, 8 plus 4 is 12, 12 plus 4 is 16, and like that. And also here we have 1 times 4. This is 2 times 4. This one is 3 times 4. Here is 4 times 4. So multiply by 4. 5 times 4. And 6 times 4. So for that one, using what I have on top, adding 4. This is x such that x belongs to natural numbers. This is what I have in general. We have xn equal to xn minus 1 plus 4. Meaning that, for example, the second number we have is xn, and this is xn minus 1. Xn minus 1 plus 4 is equal to xn. An example for that part is, for example, n is 1, x1 is equal to x1 minus 1, we have 0 plus 4. So that is 4. So meaning that the first one is what we have here. N equal to 2. So x2 equals to x1 plus 4. And x1 is 4 plus 4 is 8. Now the third one, x3 is x2 plus 4. And x2 from previous part is 8 plus 4 is 12. So you have 4, 8, 12. All these first, second, and third number. So it works like that. So meaning that this is set builder for this part. And also I want to make that easier. Another way is x such that x belongs to natural numbers and x is multiplied by 4. Or you can also say x such that x belongs to natural numbers and x is divisible by 4. So all these are divisible by 4. I prefer this one. So all of these are correct. So either that one, this one, or this one. Now example number 4, use the following graph to write a set in raster notation. So here is our graph. Here, horizontal line, we have days, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And here on vertical line, number of cakes sold. So this graph is cakes sold for by the bakery. Part A is set of days in which at least 8 cakes were sold. So at least 8 cakes. Here we have number of cakes and at least 8 cakes sold is, we have this one, it's Monday, this one here. So we have all these as Monday, Thursday, Friday, Saturday, Sunday. We have roster Now, part B, set of days in which less than 9 cakes were sold. So here is 9. Less than 9 is this one, and this one. So we have Monday, Tuesday, Wednesday. Now, part C, set of days in which the number of cakes sold was between 7 and 17. Here is 7. Here is 17. So between these, again we have this one. We have this. And we have this. So we have 3. There's Monday, Thursday, Friday. Part D, the set of days in which the number of cakes sold was more than 19. So more than 19, 19 is here. More than that, we have nothing on top, meaning that here is empty set. So the answer is empty set. Is this one. This is what I mean, but the answer is that one, because we have to show it set. So these were answers. Now example number 5. Determine whether each statement is true or false. If false, state reason. Here we have 9 belongs to 1, 3, 5, 7. Obviously these are odd natural numbers, and 9 belongs to that one, because here we have 9 and after that 11. So this is true, because 9 belongs to odd natural numbers. So that is here. Now part B, this set, and inside that we have X, if asking if that is part of this set. Here inside this one we have X, but we do not have this set. So the answer is false. The answer is false. And adding note here, the set. This one is a set, and set cannot be an element of another set. So that's why this is not correct. So, but if you had, instead of this, I'm writing that part here on top because this is not exactly the same as that one. If you had this one, so this means it doesn't belong to. Since it says doesn't belong to, the answer for this one would be true. So that is true because it says doesn't belong to, but here they have belongs to, and that is false. Now part C, here we have n. Do we have n inside this set? No, we don't have n here inside, meaning that this n doesn't belong to this part, so the answer is false. N is not in the set. Or n is not element of set. Here is 24 belongs to 2, 4, 6, 8. These are even natural numbers. Obviously 24 belongs to this set. And here is true. These are even. These are even natural numbers. That's why 24 belongs to that set. Next one, x doesn't belong to the set. Here we have x inside. This is not true because x belongs to the set. So here is false. So once again, what this means is not an element of the set. The answer is false. Why? Because we have x here inside. Let's add another one here. Another example based on what we have here. What if you have x belongs to? If we have that one, and since we have x here inside, meaning that this is true. So x belongs to this set. So this was another one. Let's say this one is F. Number 6, determine number of elements for each one. Here is number of elements in this set is equal to, so number of elements set A, counting how many members we have. We have 8. So that is the answer. Next one, how many members we have here inside. Since I don't know what that is, A or B or C or whatever, I'm writing this way, and I'm writing exactly what I had here. So the number of elements in this set is equal to, we have nothing inside, so that is 0. Next one, here again we do not have, if that set is A, B, C, or I'm writing exactly what set is. It's 1, 2, 3, 4, 5, 6. Now how many we have? Obviously we have infinite. So infinite elements in the set. And finally part D, x is between 3 and 12. So writing roster form. So roster form. starting with 3 because that x is equal to 3. So 3, 4, 5. And this is not equal to 12, so we do not have 12 here inside. This is roster and this is set P2. Now finding what the answer is, number of elements in this set. So I'm writing exactly like how here. If, for example, we had this A equal to that one, B equal to this one, C equal to this one, instead of writing that set here inside, we were able to write, like, for example, this number of elements in C. So that way is easier. But since we do not have that for here, I'm writing this way. Count them, how many we have. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the answer is 9. Cardinality is 9 for this part. So the first one we got 8, here 0, infinite, here we have 9.